So welcome everyone. Thank you for coming to this seminar of reinforcement learning, ICARL stuff that we're going to have a bit different today. We have a very special guest. So as you probably saw in the description, we're not going to take today so much of a reinforcement learning only focus, but it's going to be also from, agents from a different perspective. We lose Cheke, who is from University of Cambridge. And yeah, I think just to mention that for the new ones, before you leave after the talk, we usually have some networking time with food provided by our sponsor, DeepMind. And with all that said, Lucy, the floor is yours.
Thank you very much. Thank you very much for inviting me to come to speak to you today. So I'm going to probably give a talk that's a little bit different to some of the other ones, but it's still going to be more or less about reinforcement learning and AI. So I come from an animal cognition background, or we also call it comparative cognition, comparing different kinds of minds across the animal kingdom. And the big challenge this field has faced over the last 150 years is that intelligent-looking behaviors appear throughout the evolutionary tree. And some of them are the kind of obvious ones, tool use in apes, that you think, well, that intelligent behavior comes with an animal that I otherwise think of as intelligent. But some of them are appearing in places you wouldn't necessarily expect to see. So for example, this is a bolus spider, and a bolus spider produces a sort of lasso out of web, which it uses to catch flies like this. This is a archerfish. The archerfish sucks up water in order to fire water at insects to knock them into the water so as to be able to eat them. These are really cool, intelligent-seeming behaviors in animals that we otherwise don't necessarily think of as very intelligent. So it's always the important question, whether or not you think of that particular animal as generally intelligent or not, to ask the question of, like, yes, it seems intelligent, but how do we know if it is? Yes, I can see a dog driving a car, but I know that dogs can't otherwise drive cars. What's happening outside to allow this dog? What training and scaffolding has occurred to allow this dog to drive this car? And we find across the animal kingdom that there are a number of different ways in which we can produce behaviors or see produced behaviors that seem really clever, but actually might be the result, for example, of what we call a fixed action pattern or an instinct, something that's built in, hard-coded, or a physical adaptation. The body is built in such a way that that's just what it does. Associative learning, reinforcement learning, or specific training, which obviously is a form of targeted reinforcement learning. And so what we get often is a situation where you might see a behavior that's even superhuman, that is far better than a human could do in that particular task, but being produced by another species that theoretically is far less intelligent. So you have lots of examples of pigeons beating undergrads at stuff. That's like a classic headline we love. But there's, in terms of more kind of ecologically natural evolutionary processes, you have animals, for example, like the Clark's nutcracker. A Clark's nutcracker survives over winter purely on seeds that it has buried through the month of September. So over something like 9 months, and over hundreds of thousands of square meters, and that large areas, it will remember enough locations of things it's hidden during the month of September to then survive until May. That's something a human can't do. We see the same sorts of challenges and the same sorts of things when we're looking at AI. In AI, it's really common to see things that come across as superhuman, super intelligent. And obviously, this has been a big deal over the last few weeks, and the last couple of years, particularly with language models. But this is something we've been seeing, since Deep Blue beat Kasparov at chess. We see AIs that can do incredibly complex, intelligent-looking things. But just as we have with a lot of the animal examples, in many cases, although we can have an argument about whether or not this is the case for language models, let's forget those for a second. In many cases, what we get is very complex and very impressive, but super specific. Yes, Deep Blue could beat Kasparov at chess, but Kasparov could also find his way back to his hotel room, put the kettle on, infer the existence of a bathroom, go to the bathroom, remember that his bedroom still existed while he was there. And all of these things, as well as being good at chess. Deep Blue, not so much. So it's not computational power per se that makes intelligence, but flexibility. I don't think that's news to anyone here. What's interesting is that we have very similar challenges when exploring intelligence in different animal species as we do when trying to understand it within AI. So we have slightly different terms, but they come across as more or less the same sort of stuff. So in animals, we have instincts, stuff that's built in. When you see X, when you see stimulus X, do behavior Y. And we would say in AI, that's a hard-coded thing, right? Similar sort of a concept. In animals, we have things that are just reinforcement learning. Learning that when you see X, you do Y. And the same just reinforcement learning in AI. These very simple, inflexible behaviors can produce very, very complex, intelligent-looking, clever-seeming behavior. But they share certain features that are hallmarks of this problematic inflexibility. So, for example, the learning can be overgeneralized to things that share features completely inappropriately. So in animals, for example, here was a dog fetching a stick to a statue. Here was a pandemic toddler. Just to make that video go again. Going up to all rectangles, pushing them and then doing this. Because it doesn't understand about hand sanitizer, or hanitizer, as my pandemic toddler called it, but does understand that what one does with rectangles is we goes and presses them and does this. We have, for example, a herring gull chick that is born with the tendency to peck red. And that is because on the mother's beak, there was a little patch of red here. And if you peck that, the mother will regurgitate food. But if you give the herring gull chick a choice between its actual mother and just a really big bit of red, the herring gull chick will starve to death pecking that bit of red forever. So we have the same sorts of problems. Yes, the moth is guided by the moon, but a fire right nearby is like a super stimulus. So let's fly into that instead because it's better. But we see the same sort of thing when we're seeing whether or not an AI that's been trained, for example, to recognize pictures of robins that can overgeneralize this learning to something that, from a human eye, does not look much like the trained stimulus. And we have the opposite problem. We have failing to generalize to things that it absolutely should be generalizing its learning to. So again, in the case of the herring gull chick, if you take its mother and you take the red off, it will, on the other hand, starve to death not pecking at the beak to receive the food because it doesn't see the red. You have the situation that, in this case, it was on 7 Worlds, 1 Planet, that the albatross chick fell out of the nest and was about 3 inches from the place where it was before, begging and crying to be fed, and the mother acted like it had disappeared, like there was no chick at all. Then again, you see the same sort of thing. You add, 0.00% noise to a picture, a perfectly well recognized picture of a pig, and a image recognition model will suddenly be like, well, I have no idea what that is. You added 0.005% of noise, and now it's just unrecognizable. And all of the stuff that used to be really meaningfully difficult for AIs, but obviously no longer is, within the kind of recapture sort of the remit of, you take this word and you just make it slightly wibbly, and now it's completely unrecognizable as a word. Now, obviously, stuff's moving on really quickly in AI, but some of these kind of difficulties are really, really entrenched and difficult to get around. And one of the reasons that it's really difficult to kind of make sure that you're seeing an intelligent behavior is that both AIs and animals are really good at cheating. If they can find an easier way to solve a problem, they will, because reinforcement learning is excellent at doing that. This can range from obvious brute force, and that's literally brute force in the case of many animals, ways of approaching things, like a Kia or a chimpanzee is strong. It is easier for them to just smash it. If smashing it works, they'll do that instead of having to think. But shortcut strategies can take advantage of loopholes to maximize a reward. This is, I'm sure a really famous example that you're all familiar with, but you get exactly the same sort of thing when you're working with animals. You can also find that whilst they are doing something clever, it's not the clever thing you were going for. So in this example, this was a numerosity study with bees, where they were trying to understand, can bees count? And the bees were performing brilliantly well. The bees could count amazingly, until they did enough control studies to show that bees were really good at detecting amount of contour length in a visual stimulus. So as soon as you made the contour length not correspond to the numerosity, they stopped being able to pass the task. It's not that they weren't doing something clever, it's that they were doing a completely different, quite clever thing to the thing being tested. So just as the challenges of understanding whether or not something's intelligent or whether or not a particular capability is being employed to do a particular task is similar across understanding animals and understanding AIs. We can take advantage of the tools and skills and expertise that has been developed over 150 years in animal cognition to try and make similar progress in trying to understand cognition in AIs. And really this comes down to the important points of the design of the tasks you use and paying really strict attention to the type of training and to the reward structure. These will all be very familiar concepts to you because the challenge and the answers are the same. So what we do in animal cognition is generally you find a behavior that you can work with. It's not whether or not you can train the behavior in the first place, it's whether or not the behavior is there and you can use it. So for example, this is string pulling. This is something that you can either get naturally, get spontaneously, or train in a large number of different species. Pull this string to get the thing. So you can see here a bee pulling a little cup of sugar water towards itself. The question is, not so much what does this behavior tell us about the animal, but what variants of it can we give them to begin to understand what precisely is being understood by that animal? So I'm using string pulling as an example because this is an example of the kind of study that we would do. So here we know that the animal, in this case it's a scrub jay, can perform behavior, and we're trying to ask, what do they understand? Do they behave appropriately in different variations of this task? And how can this inform us as to what cues they're using and what they understand by them? So what we can then do is, by varying the type of challenge across tests, we can say, right, if they have hypothesized level of understanding 1, then I would expect this pattern of performance. And if they have hypothesized level of understanding 2, I would expect this pattern of performance, and so on. So the specific example of this study, we had different arrangements of the string that challenged that could be passed or not passed depending on what understanding the birds had of the situation. So our one hypothesis is that they were just pulling the string nearest to the food. Like if you had a choice of 2, so here is one string with food on the end. So if you do that, if you pull that, it means you just can pull string. But imagine here's a choice where there is 2 strings, one has food on the end and one of them doesn't. If what they're doing is just pull strings, shouldn't matter, they will just pull at random. But if they have at least paid attention to where the food is, they should pull the string that is attached to the food. However, that doesn't mean they understand anything about connectivity. For example, they might be pulling the string that is closest to the food, in which case they should pass this, but maybe not pass something like this, where actually the string end here is closest to the reward, but is the wrong one. So you can then make a prediction across these different levels of understanding about what pattern performance you'd expect to see. And so that's what we did. And so this is just an example. We found that the scrub jays could do these 2 sets, but really weren't able to do these ones. So we kind of then conclude that yes, what they were doing is they were just saying, like, pulling a string behavior, pull string, perform on string nearest to reward, get reward. And then as soon as that stopped being a good strategy, then they stopped being able to perform the task properly. Okay, so that's an example of the kind of thing we would be doing in animal cognition experiments. How does this relate to AI? Well, over the last few years, we've been building this platform called the Animal AI Environment. And the aim of this platform is to provide an environment in which we can build tasks designed and originating from animal and developmental child cognition and start to explore the abilities of AI agents, mostly reinforcement learning AI agents, on these types of tasks using the methodological approach that we would use within comparative cognition to begin to understand what type of mind are we dealing with different kind of AI models, particularly reinforcement learning AI models. So just to give a quick introduction, this is actually the kind of old version of animal AI, and there's a few new things now, but this is kind of mostly how it is. So what you have here is a really simple environment. It's 40 by 40 always. There are some objects in it that are solid, can't be moved, others that can be pushed and pulled. Just pushed, don't know why I said pulled. And there is, the main target is this green sphere. A big green sphere is a lot of reward, a little green sphere is a little bit of reward, and it ends the session. There's also the yellow sphere, which you can get as many, which doesn't end the session, but is otherwise just as rewarding. And then there's the kind of the black, the red poison, if you like. It's still a sphere, but it's red and it kills you. And then there's lava. The floor is lava. The red floor is lava, it kills you. The orange floor is like really hot, but not quite lava. It hurts you the longer you stay on it. And the idea is that there's a really finite number of reliable objects that appear within this environment, and you can train in a kind of a finite set of objects and reward structures and so on. And what we did is we ran a competition in 2019. This was a long time ago now. Moving on automatically without me. Where we basically said, look, here's the environment. Here are the objects that exist. These are the rewards.
Maybe we should stop a moment. I was trying to make it wait, but it's not letting me. Your computer.
Ah, okay.
Look.
You alt tab to select it.
Yeah, the thing is, when I come here, yeah, just let me.
Maybe it's not on the laptops, maybe on the station.
Yeah, maybe.
It looks like Windows, no?
It looks like Windows, yeah.
I think it's because it's maybe not getting its power. Oh no.
No.
No, it's just classic Windows.
Classic Windows.
This is promoted by Ubuntu.
Wait an hour?
That's what I'm trying. The thing is,
Oh, it's not there. I see.
it's not there.
I think maybe the projector actually is only on the screen. That doesn't make any sense.
Yeah, that's why I didn't see it. It's not up there.
No, it's not this one either.
I was moving that mouse with this. It's just that like now. Like, can we? No, this mouse is not moving that.
So which mouse did you just move?
I mean, before it was this mouse that I was trying to get. None of the mouse is moving.
I think we just ignore it. I think the worst case scenario is that this projector will turn off.
Yeah, well, let's skip with that.
That's not the worst case scenario, you know it, but it is a likely. Yeah. The human animal clearly can't. So yeah, shall we just see what happens if we keep going?
Yeah.
Let's wait to see.
I think we're not on.
Yeah. So which one is it? So just
Yeah, yes.
this one.
Yeah.
And, come on, you can do it. And it's
Oh no, other way around again.
And, yeah, and display settings. So
Okay. So continuing. So what we told people was basically like, here's the environment, here are the objects, here's the reward structure. Train an agent to survive here. We're not going to tell you what the tasks are. And sorry. And the point was that what we're trying to assess is in the same sort of way we'd assess an animal. They don't get born into cognitive tasks and train on those throughout their lives. They live their lives, and then you take them out of their lives and you give them a cognitive task. And so we were trying to match this with this competition to say, right, train your agent to survive in this very simple world with lots, make whatever arrangement of objects you like. Train them until they're good. Then give them to us and we'll test them on our cognitive tasks. And then we had around 300 cognitive tasks, all taken from the animal cognition literature that fell into different vague categories. So we had kind of different kinds of mazes, detour tasks, delay of gratification, numerosity, tool use. And I'm not going to kind of go into much detail about this. These were the winning entries. But what you can see is that in general, we got really quite good performance across some of these sorts of areas. So, but very simple mazes and like, here is an open field, there is the reward, go get it. And really very poor performance in some of them, such as like tool use. The point of this is that this kind of platform allows the basis for meaningful comparison. So as a proof of concept, we then took a group of 6 to 10-year-old children and tested them on the same tasks, just to see, okay, obviously this comparison has lots of ways in which it's not a fair one. Children at age 6 have been trained a little bit more than a reinforcement learning agent just submitted to this competition. But can we start to meaningfully make this comparison at this point? And so, for example, in this study, this was run by Cosi Futaris, which we tested 6 to 10-year-old children across these tasks and compared to the agents submitted to this competition. And reassuringly, what we found was that on these very, very simple tasks, where all you have to do is navigate to the reward in an open field environment, actually the agents were pretty consistent with the children. There wasn't much to differentiate between them. But it was really interesting as soon as we got to anything cognitively complex. So we'll start with something that for a biological agent is relatively simple, object permanence. So this is my 1-year-old daughter. And this is, I would like to tell you it's an agent. It's not, it's me playing the game. But this is the kind of task that we're looking at. So you see an object roll behind an occluder and you have to go and get it. This is the kind of thing that is past but around 8 months in babies. Day-old chicks are born with this ability. This is biologically quite a universal skill. So the best 10% of agents solved this, the best 10 agents solved this about 8.6% of the time. The very, very top agents solved it 25% of the time. These are actual videos of the agents from the competition and their behavior. So that's the agent there. 25% is how often you solve it if the strategy of always go left is employed. No agent demonstrated this skill. And if you look at the children compared to the agents, there's a really, really, really massive difference. Even if you only take the 2 that basically won on different criteria, there's a massive difference in performance between them and the children. That's not unexpected, right? The point is that even when both fail, there is an observable difference between the children and the AIs. So this is a child failing, 9-year-old failing, and this is an AI failing. I'm sure you're all familiar with the concept of just going around in circles. But you can see in both of these fails, a notable qualitative difference in the way the behavior is performed. And this is just a general point that failure tells us as much or even more about the nature of the intelligence performing the action than success does. So here are, again, a bunch of, oops, I'm gonna get the roughed. Can you click on the roughed lemur?
I cannot see the mouse here, to be honest. Here. Okay. This one?
The black box. Yeah. So with the same task, so again, these are failures, different failures across the same task. We can understand a lot about what's going on by seeing what failures are produced where and in what way. So here we can see that my 1-year-old, this AI agent, and all of these animals in this video are all failing to understand that a barrier, a transparent barrier between me and the reward means I have to go around it. Okay, so it's important to understand to be able to differentiate between stupid and intelligent behaviors. Fine. But the thing is, there is very rare, both in nature and within AI, for any given individual to be entirely stupid or entirely intelligent. We are both stupid and clever in equal measure, just in different places. So what's important is not just to be able to differentiate between specific instances of, if you like, stupidity and intelligence, but what is the unique pattern of stupid and clever across many different challenges of a particular individual. So you can think about this as a cognitive fingerprint. What is the cognitive fingerprint of a human compared to the cognitive fingerprint of a parrot, compared to the cognitive fingerprint of PPO? These are likely to be very different, but just saying, yes, this one did better than that one on this task tells us very little about what the nature of that difference is. So the way in which to understand these cognitive fingerprints again relies on these really fundamental principles that we get from comparative cognition. You need to have really good definitions of the capabilities you're investigating and an understanding of how they relate to one another. You need to have carefully designed tasks that actually assess them, and then robust evaluation across diverse contexts that allows triangulation across different assessments. So I'm going to tell you a little bit about a project we've been doing the last couple of years called Recog AI, robust evaluation of cognitive capabilities and generality in artificial intelligence. And what we're trying to do with this project is that we're trying to, first of all, create these really, really large, comprehensive batteries of cognitive assessment within the animal AI environment that allows us to look at pattern of passes and failures across really well-characterized cognitive tasks. And these can be then kind of divided down into different levels of detail. So for example, you might have the capability of object permanence as a kind of broad category. Then you can break that down into different individual skills, and so on and so on and so on until you get to instance levels. So this is this kind of task that's presented in this kind of way. That wall is red, the rewards on the left, that kind of level of specificity. And what you can then do, so this is just some examples from the batteries we have. We have two batteries at the moment. One is on basic navigation and object understanding and affordances, developed by Naya Ruta, and one on object permanence, developed by Cosi Budaris. And what you can then do is, because you need to develop the metadata so that you know for every individual instance from these batteries what challenges are inherent within that. So you can start to say, right, I want a series of tasks that challenge the ability to, like, these are animal AI specific things, like that, to climb ramps and to avoid lava and to get multiple rewards before the end of the session. And then you can know exactly which tasks across multiple different types of environment and types of tasks challenge those abilities. And what this means is that you can start to get, once you've tested your AI across this battery, instead of just having, well, they perform 66% or they perform 22%, you can start to show the qualitative difference between two AIs that might perform exactly as well as one another in terms of aggregate performance, but fail on very quantitatively different things, so that you can understand not just that they are medium or that they are bad, but in what way they are good and in what way they are bad. And then you can begin to systematically vary the cognitive challenge so that you can begin to say, what level of this cognitive capability do they have? So we have done a number of different approaches to try and kind of explore this sort of concept. And some of these we've done using the data that we got from the Animal AI Olympics competition. So for example, one thing you can do is you can take the dimensions of variation and look at how performance varies according to the change in those dimensions. So for example, let's imagine we've got a self-driving car, and we're going to choose the two dimensions of the wiggliness of the road and the fogginess of the environment. So you might, for example, have some instances of challenge where you've got an extremely straight road on a very clear day, or you might have an extremely straight road on a very foggy day, or a very wiggly road on a very clear day, or a very wiggly road on a very foggy day, etc. And what you might get, for example, you've driven your self-driving car in all of these different situations, and you've got a success rate of 62%. It failed to crash in 62% of the instances. Now, obviously, that is a terrible self-driving car. You shouldn't drive it. But it might be that the nature of the failure falls into different kind of situations. It might be that there is one variable that is completely predictive of that failure. It's just about how foggy it is. Doesn't matter how wiggly the road is, it just can't cope with fog. It might be that there are two variables that are predictive of failure. It can do it if it's mostly straight and mostly not foggy, but if it's a combination of the two, it can't do it. Or it might be that it fails in a random way that you can't predict. I would much rather have a self-driving car that I know can't drive when it's foggy, but I know that that's when it will fail and it will not fail otherwise, rather than have one that's just as good, but I can't predict its failure rate. So this is what we try to do with the very simplest tasks within Animal AI. So navigating to the reward in an open environment. And so we've got very simple variables, dimensions that change: the size of the reward, the distance of the reward, and where it is. So based on where the agent starts. So if the agent starts here, The reward can be right in front of me, that's easy. It can be to the left and right. That's kind of more difficult, but it should be equally difficult, depending on whether or not it's to your left or your right. Or it could start behind me, and that's really hard. And what we can see is that we can show this pattern of performance across those different variables with these kind of characteristic grids. And so, for example, you can see from this, even though this is the very easiest task that almost all the agents did okay at, this is the agent that won the whole competition. This is one of the, not the worst, but one of the less good ones. And you can see that just from this grid. In fact, we can, these are not in the order I thought they were in. That's okay. And in fact, we can start to say, what do we predict to happen in new instances based on what we understand about the tasks and what we understand about the agents? So showing patterns of passes and failures is really helpful. But when you've got a small number of dimensions, you can do a grid like this, right? You've got 2 dimensions. This was reward distance versus reward size. You can put it on a grid, that's easy. But as soon as you have multiple dimensions that might vary in a non-linear way, then this starts to get super complicated. So what you then need to do is you have to have a different way of modeling this. So in our next exploration, we started to vary a large number of different variables and started to model not just the degree of difficulty of a particular variable in a kind of linear way, but to how to model this kind of pattern where you've got lots of different challenges and the tasks can vary in all sorts of different combinations in the degree to which that challenge is presented. We then build on the cognitive demands of each instance, the relationship between the cognitive demands, and the assumption that performance will relate to how much the capability it relates with that demand, to infer a cognitive profile of an agent. And we built what we call the measurement layouts, which are a hierarchical Bayesian network implemented in PyMC, which basically makes a Bayesian model that kind of fits the performance of the agents. So this is an example. So again, using this basic navigation task within the Animal AI Olympics competition and using the agents that were submitted to that and using a really, really, really simple structure where all we had was, again, reward size, reward distance, etc., the same as before. And then we had cognitive abilities that we described that an agent might or might not have. So navigation ability, visual ability, and so on. And this is how, this is, again, as you can see, it's a really, really simple model. This was a toy test case. But as you can see, first of all, we get this kind of graph of performance. So this is, for example, navigation ability and visual ability. Some are low on both, some are high on both, but some, as you can see, have quite a mismatch between them. And again, we have the case that the one that performs best across these is the one that ended up as the competition winner. But the most useful, it's nice to say, oh yes, we managed to model who did well, but the most useful context for this kind of thing is being able to say, well, actually, when you're working with existing data that hasn't been designed for this purpose, yes, you're going to have examples from across this dimension, but you're not going to have like every single instance of this kind of challenge present. How do we predict performance on missing data? And this is where this kind of model works really well, because we can do bidirectional inference. So if we take the information we have about the cognitive challenge of the tasks and therefore and the performance on the tasks, we can populate a cognitive profile of the agents. Remember, in the competition, we knew nothing about these agents. We knew literally like who they came from, and then if they happened to write a sentence about how they trained it, good for us. But otherwise, we know nothing about them. So we create a cognitive profile on them based on their performance on the task and what we understand about the tasks. We then, so we have tasks that we haven't included in the model. We then say, well, based on the cognitive profile of those agents and the challenge of the tasks and how they performed on these tasks and the challenge of the task we're now presenting it with, how well do we expect it to do? So we can then do the top-down inference. And what we find that is if you compare the predictions of the model for new instances against those produced by a simple aggregate, it's very similar for agents that are performing at about 100%, which makes sense because there's basically no variance to explain. It performs very similar for agents that are terrible because, again, there's no variance to explain. But for these agents in the middle, where they are failing on some and passing others, understanding where it passes and fails produces a much better prediction. But remember, this is a really simple task with like 3 variables. We're not expecting it to, we're expecting sort of subtle benefits above an aggregate here. But what if we move on to something much more complex? So this is testing the model against a new battery. This is the battery of object permanence tasks that we call O Piaget, and it's got something like 25,000 tasks. We didn't do it with 25,000 tasks, that's too many. But what we did is we took 3 tasks that are very, very different, but all putatively assess object permanence, but differ in the other things that they challenge. So for example, some of them have lava, some of them don't. Some of them have ramps, some of them don't. Some of them require quite a lot of memory, some of them don't. And what you can do is that you can, because we have this very, very highly annotated metadata, we know exactly what the challenges of the different tasks are. What we don't have is access to loads of AIs. So we did this instead. We split the group into 2 teams. Team A were basically mostly the psychologists. We created a list of imaginary agents with particular skills defined. We then took those imaginary agents and we said, given the skills we have, this is the data we'd expect that agent to produce. At the same time, Team B, who didn't know what we were doing, but knew that we were doing that, but didn't know what our agents were or how we were doing that, were producing a way of translating performance, producing this model, a way of translating performance into a cognitive profile. And so what we did is that we produced these artificial agents, if you like, and we didn't give any of the information about the agents to Team B. We just handed over the data. Team B then ran the data through the model and produced a cognitive profile for each of these agents. We then compared the cognitive profile that we had started with the one produced by the model to see how good the fit was. And remember, we didn't speak to each other throughout this period. And so because we're dealing with much more complex battery here, this is what the model looks like, is much more complex. And this is the pattern of performance across the produced by the model of the different agents, the different kind of fake agents that we had across these different tasks. And what we found was that actually quantitatively, there was extremely good agreement between these kind of original profiles we started with and the profiles produced by the model based only on the data. And that was even when we included capabilities that were varied by Team A that Team B didn't know existed and therefore had not included in their model at all. When we only included capabilities where Team B knew that they existed and had included in the model, then the agreement got an awful lot better. We also did a qualitative assessment, so trying to look at whether or not the kind of the nature of the agents that Team B decided. So we had different categories of agents. So there would be like a random agent that performs completely randomly, or a reference agent, like this is the one that scores 100%. This is the one that scores 50%. And then we had different kinds, such as particularly the Achilles heel agents. This is an agent that has the ability of interest. It just fails at 1 or 2 stupid things. Like it's an agent that has object permanence, but is really clumsy and always falls in the lava, or has object permanence, but has a tendency to not be able to climb ramps and stuff like that. And so the Team B then assigned those categories to the agents at the end, and then we saw to what extent those agreed. We also had really high agreement there. We then used this model to try and predict performance of these agents on new and unseen instances. And again, comparing against just the kind of model aggregates, the performance aggregates. And again, we had much, much better predictability for new unseen situations compared to just knowing in general how well that agent did. Now, obviously, this is a situation where we're on the same team and we share a certain amount of knowledge. You'd expect the agreement to be better. But in the other one, we knew nothing about the agents at all, and the agreement was still better. So we certainly think that we've got an advantage here in being able to predict the behavior of the agent in new situations. And really, that's why you'd want to be doing the cognitive fingerprinting approach in AI. Obviously, it's really interesting as a scientist to be able to understand what is understood and what is learnt by an agent. But really, what we want is predictability. If it's going to fail, we want to know where it's going to fail, why it's going to fail, and how it's going to fail. And if we understand what its capabilities are, then we understand much better what the fail cases are, and we understand where it is safe and sensible to use this system and where it is likely to fail based on the cognitive capabilities that are required for that situation. So with that, I would like to thank the people involved in the team, particularly Matt, who developed the Animal AI platform, Cosy, who's done a lot of the work I've presented, but also the other postdocs on the team, particularly John, who's done a lot of the modeling stuff, and Ryan, and Zanaya, who's got the affordances frameworks, also our funder, DARPA. And just to note that we are hiring a new postdoc at the moment. So if you're interested in this kind of work, particularly how it might apply to whether or not AIs are going to steal your job, then please do check out the link. And during questions, I'm going to probably leave that up just as a final plug. Otherwise, thank you very much.
Okay, now it's time for questions. People who are online can post their question in the chat and I will read it aloud. So anyone in person with start?
So thanks for the talk. I think I was kind of confused the whole way on how kind of the agents were trained and how come they showed or displayed such different abilities, and like, was it the goal to have a very different pool of agents, or what did you train it on? Was it some kind, everything was out of the competition, right?
The competition agents.
Yeah.
So the competition agents were the agents that were submitted by the competition entrants. And what they got access to was the environment and all the objects, and they were told to create their own training curricula. So they were all trained very differently. We know a little bit about how some of them were trained because there was the option to submit kind of information about the training, and not all of them did that, but some of them did. And as well as the kind of other kind of tweaks to the algorithms they had done. So for example, the one that won, we know that it had a bias towards going up ramps. So it had an extra, like it got rewards for vertical velocity because the programmer said, ramps, I bet that any situation, any task that's going to have ramps in it is going to involve climbing those ramps to get a reward. So I'm going to make my thing climb any ramps that it sees. And, you know, yeah, that worked. That was a really good cheat. Although there were some tasks where it just sat at the top of a ramp with the reward right there, being like, I'm at the top of a ramp. So, you know, obviously it wasn't. So basically they were all trained very differently. The idea was that we wanted it to be completely out of distribution testing, that we're saying, right, we want you to produce something that survives really well in whatever you throw at it within this environment, with a really finite set of objects and a really kind of well-defined reward structure. We reasoned that that was a doable, yet more kind of realistic, naturalistic environment. We'd probably do things slightly differently if we were doing it ourselves with a curricula, but that's what those agents were trained with.
I have heard that people have used tools from psychology, such as theory of mind, and use them to test the large language model. So my question is, if we use this animal AI test bed to apply it on the large language model, how do you think about this thing and the capability of object permanence or tool use can be largely improved or not?
There's a number of really difficult issues when it comes to large language models. I mean, obviously, the most obvious one is that this is completely non-linguistic, so there would need to be some sort of translation for the large language models to cope with that. But so to speak to your first point, the difficulty with large language models is that they've been trained on the whole internet, right? So if it is a task from psychology that has been widely used in psychology, there are hundreds of papers that describe that task and describe what you should do when you're presented with that task, literally in the training set of that model. So the paper that you're referring to, they found that GPT-3 would pass what's called a false belief task. In a false belief task, there are two people in a room, and let's imagine there's a desired object like chocolate. Person A puts chocolate into box A, person A leaves. Person B takes the chocolate out of box A, puts it in box B, person A comes back, and the question is, where does person A look for the chocolate? And the idea is that if you have theory of mind, you understand that person A, because they didn't witness the movement, they have a false belief that the chocolate is in box A, and so that's where they'll look. Unfortunately, because that is the test for that ability, as I say, it's been published hundreds and hundreds of times, and so it's in the training set. Interestingly, as soon as you do any perturbation of the way of asking the question, so what, okay, that's the answer you've given, it's box A, but what if person A was actually there for the whole time and they never missed a thing? Where would they look then? GPT-3 says box A. So what happens if person A, in fact, was told by person B that it's in box B? Where would person A look then? Box A. So they had, once, as soon as you began to actually go outside of the detail that's been published hundreds of times and ask the actual question that gets the cognitive ability, it stopped passing the task. And this is the real challenge in assessing cognitive abilities in these large language models, is that you can't just take things from psychology and test them on it, because everything published in psychology is in the training set. So that's the first thing. The second thing is, yes, it would be really cool to get an instructable AI, right? To get like somehow manage to get GPT-4 to, via some kind of text-based interface, to send its own avatar around the animal AI environment. And I think that's the kind of thing we'd have to do, is something completely novel. And it's a really interesting question, because obviously it's never been embodied. It's not experienced being in that environment. So I think you'd have to ask about how meaningful, you'd have to be very careful about the kind of questions you're asking and whether or not they were meaningful. But certainly I think there's scope for looking at how a language model can potentially interact with a reinforcement learning kind of front end, if you like. So, you know, you're giving the instructions to a language model that then translates them into something the reinforcement learning agent can understand, and the reinforcement learning agent goes and interacts in the environment. There's some really interesting stuff you could do there, but I think at the moment it's a matter of knowing how meaningful the question you're going to ask is, given what the language model's been trained on. And that's, for me, one of the big challenges trying to understand the cognition in large language models, is that they've read the whole internet, and there's very little that isn't there to let them already know the answer.
So on the point of agents being embodied in large language models interacting with environments, I remember reading a paper recently where they've literally written a text-based interface for a reinforcement learning world. So, you know, just the same way you've got these mobile apps where you chat with a character and you decide what they should do, and then it's as if they were interacting with the world. I think some people are building now interactions for just IRL worlds, text-based. So
yeah. The thing is that as soon as you make something text-based like that, you're labeling everything for them. Yeah. And that takes 99% of the challenge out. Yeah. So if you say there is a wall in front of you, you can turn left or right. You've reduced it to one state and two actions, as opposed to like thousands of states and thousands of actions that the reinforcement learning model is having to do. Because it's literally, it's pixel input. So they're having to learn about what a wall is, what transparency is. How do you describe, how do you test? Here is a transparent wall and there's a reward behind it. How do you get it? If you have to say it's a transparent wall and you can see the reward through it. Like in labeling it like that, you change the challenge fundamentally. So that's part of the problem, is in what way can you translate the embodiment into language without answering 3/4 of the questions for it through that labeling? And we can have a whole philosophical discussion about that being, in fact, the purpose of language and why we have it. That it does those shortcuts for us. It helps us shortcut the environment and to categorize things so as to make our learning easier. But yeah, like it's not a trivial matter to translate embodied into language without taking the challenge away.
Yeah, that's an interesting one. I mean, thank you for your talk overall, because this shed light on things I've been looking into for the past like 2 months. I never thought really from the animal's perspective of it. I've been looking into inverse reinforcement learning, where the objective is to infer what an agent is trying to go for, or what have they learned to maximize based on what we can observe of their behavior. How would you say this links to the different tests that you're doing? Because I can see this as you're imagining that the reward could be A, B, C, or D. Then you build tests purposefully that think the behavior of this agent would be this if its reward was that, and then you discard rewards one by one like that.
Well, with our tests, the reward is always the green ball, right?
Yeah.
It's just how you get there and what you need to do to get there. So actually it'd be really cool to be able to do the kind of inverse, the inverse reinforcement learning assessments, you know, to begin to be like, what have you learned? Have you learned to always turn left? Like, you know, this pixel over here is the thing. I need to go towards that until I see green to the left and then I turn. So I think that many of them would lend themselves to that kind of analysis. Some of them probably less so, but we're also working on the kind of data that the task output. So at the moment we know what rewards the agent gets. We know how long it took and other things like that. But we're starting to be able to kind of export things like, what choice did it make at this point? What choice did it make at that point? And what, you know, can we link the, you know, the point at which the state it was experiencing pixel wise, just, you know, at the point that it made the key choice in a series of behaviors. And so we should be able to get a much more kind of subtle and nuanced understanding of the nature of the behavior, which I think would lend itself really nicely to that kind of analysis.
First of all, thank you so much for your wonderful talk. One of my questions would be, do you in any way, shape or form randomize the tests that you present? So something like the algorithm of just always turning left doesn't work as well, and you can kind of circumvent some of this cheating a bit more?
Yeah, so so basically that's almost the whole point, that we're making, so both in terms of the generation of the tasks, part of it is absolutely making sure that for everything we can think of, we've done exactly that. There is always one's on the left, one's on the right. So this is why I say 25% is as good as you could get on that particular task for always turn left, which is, you know, better than everyone else did, because always turn left is at least a reliable behavior. And it wasn't always turn left, it was always turn left and go at this angle, and that means you bounce off and blah, 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 blah. But yes, exactly. First of all, in terms of the generation of the tasks, you make sure as many of those bases are covered. But you also make sure that you're able to, in terms of the metadata and the annotation, to know which stimuli are the ones that you ought to be paying attention to, and which ones are really like we have purposefully randomized that, you guys, like, you know, left and right. So, but for example, in our model, we have left-right bias as a, so we have, we divided the kind of features of the agent. There were capabilities, but there were also biases. So we put in variables for biases we expected to see or to develop. So left-right bias, when we're looking at, you know, just get the reward in an open field, left-right bias was something we put in there, so that we could then in the outputs say, right, this was an agent with a huge left-right bias. And again, that's an iterative process, right? You know, you can only put in the ones that you know about in advance, but then you might learn about new ones and you add them in. So yeah, it's both. It's a parallel system of developing the tests and developing the model and making sure that you've got a good understanding of the underlying capabilities, as well as both of those things that kind of allows that to go together.
I mean, it must be super difficult to meaningfully design those randomization routines in a way that doesn't change also the meaning of the test.
Yes. So some of them are really easy, depending on the task. And we have, like, we've been developing automatic generation procedures where you say, like, keep this constant, but then randomize everything else. But yeah, at the moment, it's a large manual challenge to go through and be like, oh yes, actually that one accidentally randomized everything out of meaningfulness. So yeah, I think one of the things we get from reviewers all the time is, well, this seems really labor intensive. Why can't we just automate that? And it's a difficult thing of like, yes, we should automate what we can, but actually domain knowledge matters. You need to understand the thing you're assessing, both in terms of the agent you're assessing and the ability you're assessing. And it turns out you can't just randomize. You can't automate everything. We're hoping to automate more and more and more and more, but yeah, it matters that it makes sense. So yeah, there is, at the moment, it's pretty labor intensive.
Ask 2 questions.
So I want to like understand how interesting the variation in cognitive fingerprints might be. So I guess this is like a 2-part question.
Okay.
The first part would be, do you have any intuitions on the how significantly you would expect cognitive fingerprints to vary for agents based on like changing their inductive bias in the architecture or the curriculum or like something else? And the second question is to try and guide like interest here in nature or like in animals. Do you see significantly different cognitive fingerprints or like the same animal but with a different upbringing versus different species?
Yeah. So yes. It matters a lot. Obviously, we know that training matters a lot. Like, especially when you get down to a level of detail of just like, what are your biases? What is the overfitting you have developed? So you might find that, yeah, so that there will be, when you get down to the kind of, if you like, kind of boring nitty-gritty surface details of the task, you're going to have a hugely different fingerprint based on what they've been trained on. Because if they've only ever been trained on gray environments and then suddenly you're testing it in an orange environment, most reinforcement learning agents are going to freak out, right? Whereas it might be that the algorithm has the capability to be general about dealing with changes in the environment, you've not trained it for that. So that kind of difference you'd expect to see. And that kind of difference can be, again, depending on how extreme that is, that can be the difference between it being ever able to get so far as to do the more interesting stuff, because there's always more complexity in more interesting cognitive tasks. So on a kind of boring level, yes, of course. On a more kind of interesting level, which I'm sure is what you're getting at, I think there is always the need to be able to be given the right information to be able to build the models. If you have the capability of, say, building a world model, you need to still have the right information to go in it. And that doesn't just mean amount of training, it means type of training, and it means the informativeness of the things you witness and the behaviors you happen to do in that situation. So I think that makes a really big difference in general. Speaking to the biological side, which I know a lot better, so yes, you can make a huge difference with both in terms of exposure to different stimuli and all of the same sorts of stuff. But you have, for example, the kind of predictability and the stress of the environment, for example, in the early years. So you get, for example, real differences in cognitive profile of rats that have been basically separated from their mother a lot during the early period compared to those that had kind of a mother completely available to them at the time. And that will be both in terms of, like depressive and anxiety related behaviors, but also lots of things like the tendency to react to punishment in the environment versus reward. Like the weights and the biases there are completely different. So in certain tasks, you will find rats that can never do it, never learn it, because they are so in the context of animal AI, it would be, they're so set on avoiding the larva that they will never take enough risks to be able to get the reward, which means they'll never pass tasks that's presented in a certain way. But in many cases, they're still capable, theoretically, of having the cognitive ability, but they're just not capable of showing it in any of the tests that you have. And that's where you get this kind of interaction between, well, it matters what tests you do, as well as what agent, what individual you're testing. So one of the things that I want to use this kind of approach for is exactly that kind of thing, of starting to say, right, this is the cognitive fingerprint, say, of a rat, a healthy, happy rat. Right, this is the cognitive fingerprint of a rat that is a genetic model for schizophrenia. It might be that you can then start to be like, I think actually what we've got there is that learning rate parameter. What if I tweak that learning rate parameter in a bunch of my models? Can I start to move the, if I'm happily modeling a rat, if I then tweak my learning rate parameter systematically, can I end up modeling a schizophrenic rat? And then if you can do that, you can begin to start to say, okay, in that case, that would predict that a schizophrenic rat would behave like this in this sort of context. You can take it back to the rat and say, yes, this theory of schizophrenia is right, or has potential to be right, because this was a non-intuitive prediction of the model when I had my little reinforcement learning ratty. And that's exactly what we see in the rat that has got the genetic markers for schizophrenia. So that's the kind of thing where this profiling should be able to be useful both for a number of different ways, because exactly those kinds of differences.
Okay, last question.
Have you seen a correlation between different high-level skills demonstrated by AIs? And is this correlation also found in animals?
So are you saying that do the same AIs show good performance across a number of different?
Would all AIs, for example, need to learn or to demonstrate one kind of high-level ability to be able to also demonstrate another high-level ability?
So this is the kind of, so we have been, apart from the Olympics data, we haven't done a lot of testing of different AIs on these batteries yet. So the first kind of couple of years of the project has been develop the batteries, develop the models. And the next step is like, right, bring us the AIs, and actually genuinely bring us the AIs, because this is a genuine request, because we don't have those. Like, we have a lot of the other stuff, but we don't actually have a range of different agents and models to work with. So if you think you have a reinforcement learning model that would behave well in this environment, and you think it's cool, or that it might be particularly clever or particularly stupid, like, let us know, and like we'll work with it, because we want to have this a varied population to work with. But in animals, yeah, for sure. In general, you get animals, there's kind of this, it goes into the whole general intelligence argument, right? Like, in general, you get some animals that are good at a bunch of stuff and other animals that are bad at a bunch of stuff. There are lots of cases, like I said, with the Clark's nutcracker, where you get an animal that is particularly amazing at one thing. And this is we call adaptive specializations. And generally it's because their environment is particularly tough in one particular way. And so they've had to go above and beyond in that particular context. What you find is that sometimes that means that the whole animal tends to get smarter, and other times they develop that ability and it doesn't affect anything else. And so whole theories of the evolution of intelligence have been built on these kinds of correlations. So for example, the kind of leading theory I would say at the moment is that social challenge, that the complexity of your social environment tends not to produce social ability on its own. It tends to increase intelligence generally. Whereas something like tool use challenge is much more likely to produce a really specific physics adaptation, often of the body, like hands, without necessarily also improving performance and everything else. But this is a hot debate, probably as much in biology as it is in engineering.
All right. So thank you, Lucy.
Thank you.
And
Time for the job.
that would be really nice. So we are gonna have some food now. You will be able to ask some additional questions. Next session will be on the 24th of May. We'll have Florian Fuchs from Sony AI, who will be talking about how the research engineer Gran Turismo, like an AI that was able to beat the best human drivers in the Gran Turismo game. So hope to see you all there. Thank you for coming.
What cognitive capabilities does that even require?